And we are ready for the next talk, which is about MySQL performance tuning. And while I'm doing the talk, feel free to ask any questions you have in the Q&A chat. There will be an expert available and try to answer as many questions as possible. So my name is Jesper. I've been working in various positions over the last 14 years using MySQL, and this includes years with Oracle technical MySQL support. And most recently, I'm working with Okta as a database reliability engineer. I have also contributed to the MySQL Schema and 4 MySQL Oracle professional certifications. And in my spare time, I've been working on 4 books, all with published through A-Press. And I'm on Twitter and have my own blog. So on to the agenda for today. I just have 2 items. First, I will talk about how to work when working with MySQL performance, and then I will talk about the virtue of being lazy. So when you work with performance problems, it's actually not all that different from working on any kind of troubleshooting, also taking other than MySQL products into account. So the best thing is to work proactively. The more you can work proactively rather than in emergency situations, the more calm day you'll have, and the less stressful, and you'll be more successful as a bonus. The key to working proactively is monitoring, and I cannot stress enough how important monitoring is. You can use it, for instance, to catch issues before they become an emergency. So again, that helps you being less stressful, and you can take your time to find a good solution for it. Monitoring also helps you understand what's going on, and that's not only useful for proactive work, it also will help you in those emergencies that eventually will happen, and trust me, they will happen. But in general, your proactive work should also prepare you for the emergencies. And a small example could be to have a standby replica that you can fail over to in case you, for example, have hardware issues on your primary instance. And this is a fairly common scenario that and that can help you do a quick failover in a few seconds, and then you can take the bad behaving host offline and get out of the emergency and go back to working in the calm and solve the issue. So when you're working on an issue, it's important to work systematically. And that starts out verifying what the actual issue is. And this might sound like a trivial thing, but it's often not that simple. So take a simple example. Somebody comes and tells you, MySQL is slow. So what does that mean? Is it a single statement that's taking too long? Is it the throughput that cannot keep up? Or is the issue really somewhere else? It could be the application that's really spending time wasting cycles on something it shouldn't be doing. Or it could be the network or somewhere else. So you need to narrow down exactly what the issue is. And at the same time, you need to determine what it means to solve the issue. You could say, make the statement as fast as possible, or make the throughput as high as possible, but that wouldn't mean that you would never finish. So you need to set a realistic goal saying the statement must finish in at most this amount of milliseconds or seconds, and the throughput must be able to handle some number of statements per second. And then you know when you're done, and you can maybe later get back to it and improve it further. But it's important that you have a goal for this bit of work. Once you know what the issue is, you can start determining the cause. And that's typically the most difficult part of the job. And once you have the cause, you can move on to the solution. And in many cases, once you have the cause, the solution might seem trivial, and you might even start to wonder, what was all the fuss about. But there are gotchas with solutions as well. You might need to implement a solution in a different part of the stack than where the actual problem is, because you might not be able to fix that problem. Or you might need a stopgap measure and then another solution for the more long term. So keep your mind open for this and determine how you can best solve your problem. And then you implement it. And the important thing when you implement it is, of course, test and also write down the exact steps you're doing. This will help you implement the solution in your production system exactly how you did it in your testing and staging system. And if some unexpected side effect turns up, you can go back and look at exactly what did you do, try to reproduce it, and if needed, it can also help you roll back the steps you did. I mentioned that verifying the issue and determining the solution, that you should look at different places for where the issue is and where you can implement the solution. So it's important that you consider the whole stack. This is a simplified picture. There's actually more to it than these 5 layers. But the application sends statements through the network to MySQL, and MySQL interacts with the host through the operating system. And you might have hypervisors, and the host might be a virtual machine and so on. But this should get you the idea of things are related. And if you only look at MySQL specifically, you will miss out on a lot of important issues. And to illustrate this, let's take a look at a real case scenario that I worked on earlier. So this was an application that was ported from using SQL Server to using MySQL. And after the porting had been done, the user started to report that MySQL returned errors. And since it was a ported system and there wasn't actually much changed in the application, it was kind of obvious that MySQL would be the point of focus, and you would think that this was a MySQL issue. So what was the error? The error was that the application host got blocked because of too many connection errors. This happens when there's a bad handshake during the authentication. And you can, for instance, see this if you use a software and connect to the MySQL port, and the software doesn't talk the MySQL protocol. So Telnet can be used to simulate this. So this screams at somewhere between the application and the network. But if you just look at that, you would probably get on quite a long wild goose chase. And you might even try the solution listed in the error and flush the host. But that would just temporarily fix the issue, and then it would come back. So here it's important to look into the rest of the system and see what other symptoms there are. And one that stood out was a very long-running query. And not only was it long-running, it examined millions of rows. Furthermore, if you kept looking in the process list, would actually see there was 50 of them. And I'm not talking about 50 variants of it. It was 50 identical copies of the same statement. So what was going on here? It's starting to become more complex of a problem. Finally, it also turned out that the application crashed once in a while with out-of-memory errors. So here you can see already at least 3 layers are involved. So what was the cause? Well, actually the cause turned out to be really simple. The framework had a bug. So when it was using MySQL as the backend, it missed out on a where clause for this particular statement. And so the statement was actually wrong. And furthermore, the application gave up waiting for the result. And then it would resubmit it and so on until there was 50 copies of it. So MySQL was running in a small virtual machine in the cloud. So also the data didn't fit into the buffer pool. And this was not a frequent running statement. So the first copy of the query would start to read all the data from disk. The next one could benefit from that and reuse the data that was already in the buffer pool until it caught up and so forth. And in the end, actually all 50 copies would finish within a couple of seconds. And because of the missing where clause, it would also send huge result sets back over the network. So in this case, again, the cause was found and the solution was really easy. Just upgrade the framework where the bug had been fixed. So talking about missing where clauses and doing too much work, I'll turn to the second part of my talk, which is about being lazy. So when I started at university, I studied chemistry. And on the first day of the introduction week, one of the professors stated that a good chemist is a lazy chemist. And yes, I've tried to live by that since, but it can actually also be applied to databases. So rephrasing this a bit, make MySQL work smarter, not harder. So as we saw in the example, missing where clause is a bit of a killer. So make sure those are present and correct. And it might sound far-fetched and a rare case, but it happens much more frequently than you think. And my next case study will show another more subtle example of this. And missing where clauses is a double whammy because it doesn't only affect the statement itself, but because it consumes CPU, pulls data into the buffer pool and so forth, it also affects the rest of the statements on the same system. And a great way to, assuming that your where clause is correct, a great way to reduce work is also to use indexes. So indexes, you can think of those as shortcuts to find the rows that you need. So kind of looking up in the index in a book to know which page to start looking at rather than have to read through the whole book to find the topic of interest. That said, there are some gotchas with indexes. So you might think you have the correct index, but it cannot be used. A common issue is if the columns you have in your where clause does not form a left prefix of the columns in your index, then the index will typically not be used. And I'll show an example of this as well. There could be data type or character set mismatches, or you could have functional dependencies. On the more positive note, you should also take a look at the release notes and see what kind of new features are implemented in MySQL. And MySQL has 8, for instance, have a range of new features that can reduce the amount of work being done. I'll talk about hash joins and common table expressions later in this talk. And finally, talking about MySQL, choose the best schema for your work. This includes a sequential primary key for all your tables and choose an optimal data type. And in short, that would mean use a native data type for your data, integer data type for integers, for instance, JSON data type for JSON documents. And something like integers comes in various sizes, tiny int, small int, and big int. Choose the size that corresponds to the data you want to use. But looking at being lazy, also consider that changing the size of a data type typically involves rebuilding the whole table. So bear in mind what you think you will need a little bit into the future so you can avoid doing unnecessary table rebuilds. And finally, the best statement of them all is the statement that is never executed. So consider what you can do to cache data results and reuse them so you don't keep executing the same statements over and over. So back to the where clauses and indexes that cannot be used. So this is another real world example. where the symptom was that the monitoring system reported a very high CPU usage on one of the database hosts. And this was a monitoring solution that allows you to collect what queries are executed during a given time frame. And I really recommend you to choose a monitoring solution that supports this. So it was easy here. We just looked at the time frame where the high CPU was and looked at what statements were executed during this time. And there was particularly one that dominated. And this was a simple query joining two tables. And when we looked at it, the where clauses and join conditions looked all correct. It actually also returned the correct results. So what was the issue? So it came out that this was these tables were prepared for sharding. So there was a column that was used for sharding, and then all indexes that was relevant for this statement had the sharding column as the first column in the index. So in this case, let's say the sharding column is group ID, and use ID and status was used in the where clause and join condition. And here's the issue. So while the where clause actually did take into account that this sharding column existed, it was only added for one of the tables, the one that was chosen to be the first table in the join. This other table didn't have it. For human, this looked correct because knowing the schema, knowing how the application worked, it would know that the group ID, the sharding column would be the same for the two tables. But MySQL had no way of knowing this. That would require something called a natural join. So the end result was no index was used on the second table, and a full index scan of more than 1 million rows were done on the second table. And that's for every single row found in the first table. And that caused the high CPU. And this is a good lesson. If you ever see high CPU, start thinking of, could there be some statement that either doesn't have the necessary where clauses or cannot use indexes? There might be other reasons, but this is a very typical example of high CPU. So I mentioned joins. So how does MySQL join two tables? There are two ways, two essential ways that MySQL joins tables with some variants. The basic way to do it, and what has been around for as long as I remember, and possibly all the way back to the beginning, is the nested loop. This is very simple. You take a table, find the rows you need, and for each row, you look up the matching rows on the next table and so forth. You can do this with or without an index. And if you look here, what is in red, that is an optimizer hint, and that's another great feature in MySQL, that you can use optimizer hints to affect how the optimizer will get to the execution plan. And here, disable indexes explicitly, because MySQL will obviously think it's better to use indexes than not indexes. And I disable something called the block nested loop. So that's the next variant. The nested loop without indexes would simply do one row from the first table and then scan the next table, next row from the first table, and so on. That's very inefficient. What block nested loop does is that it reads a batch of rows, so it reduces the number of iterations through the inner table and the join. This has actually been removed in the latest couple of releases, and because there's been a new player in the game called hash joins, which is the last example I have. So how does this compare for this statement that finds all cities in Asia? And if you want to try this after the talk, it's using the World Sample Database. So I executed all 4 of them and used the syssession view to get the number of examined rows and the execution time from the performance schema. So as you can see, the nested loop with index examines the least amount of rows, and nested loop without indexes is by far the one doing the most work and is also the slowest. Regarding the execution times, I want to mention here, this was done on a virtual machine on my personal laptop. So mileage might vary, and the interesting thing here is really not the absolute times, but the relation between them. So you can see the block nested loop is around 50% slower, but interesting here is the hash join, which also disabled all indexes, and the nested loop with index is around the same time. And to understand this, you need to think of how indexes would work. So when you do an index lookup, you first look in the index, and then you need to move on to the primary key where the row is stored. So that's 2 lookups for each index, for each row. Whereas when you do disabled indexes, you do full scans that is all sequential. So indexes tend to be random IO, scans tends to be sequential IO. And even when it's an all in-memory workload, that can be seen in the execution times that the scans fare much better than you would think by just looking at examined rows on its own. So how do you know which algorithm is used? Well, for execution plans, you need to turn to Explain. Explain is a really powerful tool, and you should really spend some time on getting to understand how it works and how to read its output. So there are various formats you can use, traditional to get an overview, JSON to get as much detail as you can get. And in MySQL 8, there's also a new format called the tree format. And this is related to the new iterator executor based on the Volcano executor that's been implemented. And I'll show an example of how the tree format looks. It can be quite intuitive to understand the execution flow. Finally, there's Visual Explain, which is a part of MySQL Workbench, and it uses the JSON format to generate diagrams, as you can see here on the right. So you have the 2 tables, the country doing a full table scan, and this is for the index nested loop. So it does a non-unique key lookup on the city table using the country code index. And you have 239 rows estimated. And it's important to note here, these are estimates from the country table, 17 rows for each of the lookups in the city table. And it is estimated that it combines to 610 rows total. The decimal numbers to the left are cost estimates. So MySQL uses a cost-based optimizer. And it works by estimating the cost of the various parts of the execution plan, and then it comes up with a total number. And for most statements, there are various ways MySQL can execute the statement to get the right result. And it will estimate for most of them and then choose the one with the lowest cost. But then how does these estimates actually come out? How good are they? And it used to be very difficult to say, yeah, you could start to look at the number of examined rows and see how that looked, but it wasn't really satisfying. But that has been resolved with the explain analyze statement. And that's also a result of the new iterator executor. So let's look at an example of this. So explain analyze uses the tree format. And I apologize here that the font size is a little small. I try to avoid too much wrapping. So I hope you can follow along. So for each line, there are 2 set of parentheses. The first parenthesis is the same as you just get in the plain tree formatted explain output. And these are the estimates. So you have the cost, expected number of rows, and then the second parenthesis is actual statistics collected by executing the select statement and then stripping the result set so you don't see it. You just see this output. And there are two timings. The first is for the first row fetched, and the second timing is for the last row, and then the actual number of rows. So you can see here, it is estimated 610 rows, but the actual number of rows is almost 3 times as much. So it's not a terrible good estimate in this case. And then it does, you can see that it does a table scan on the country table, apply the filter, which is not using an index, and it returns 51 rows for the country table. And then it does an index lookup on the city table using the country code. So this is much the same information you also saw in the visual explain. But this is also where you can start to see why the index lookup is not super efficient. Because if you look here for the city table, 51 loops. That's one for each of the rows in the country table. And for each loop, on average, it finds 35 rows in the city table. So that's a lot of random IO that comes out of that. And that's why, even though it does the least amount of work, it's still not faster than the hash join. So how does the same look for the hash join? So I won't go into detail here, but important thing to look at here is loops 1 for the city table. So it actually swapped the order of how it of the two tables, and also one loop for the country table. So it only does one loop of each, and it just reads everything. And that's why it's so efficient. So let's talk a little bit more about the hash joins. They were introduced around a year ago, and has later been extended to support virtually all join operations. So in 8.0.20, they completely replaced the block nested loop. It works best if you can read as much into memory as possible, and it uses the join buffer for this, which is actually the same as the block nested loop did. So you might need to increase the join buffer to get the best performance. And note it uses a 1 join buffer per join, not per statement. It never uses indexes, so histograms is something to consider for these tables. And it's the great thing about the implementation is that it supports spilling over to disk if the join doesn't fit into memory. So there's not really any limitation in that sense on the size of the tables that you can use. And it can be really a lot faster than block nested loops. So yeah, if you don't use 8.0.18 or later and you have unindexed joins, upgrade, and so you can get advantage of the hash joins. So this sounds like you should always use hash joins, right? Well, not so quick, because the example here didn't actually have a very good index. There was too many rows for each index value. So a more selective index would still outperform hash joins. And because it needs memory to work as efficiently as possible, hash joins requires more memory than the nested loop. And the world sample database is really small, and it doesn't really matter. The default join buffer was big enough, but for real world cases, you'll need more memory. And because it does full table scans, there are 2 other side effects. First of all, it moves more data into the buffer pool, which pollutes the buffer pool, might reduce the hit rate, or you need a bigger buffer pool. And it takes more logs. So don't discard indexes just yet, but definitely hash joins are really great for cases where it doesn't make sense to have indexes. So the last thing I want to mention is common table expressions. You can think of these as a named subquery, and they're defined with the with clause. The one of the great features of common table expressions is that unlike normal temporary tables and subqueries, you can reduce them within a query. So just do a quick example to show you how this works. So using the Sakila sample database, we find the sales for each staff each month and the difference from the previous month. So each subquery calculates the monthly sales, and it's completely duplicated here. So if you need to make an edit to it, you need to remember to do it both places. So it's both more work, more error prone, harder to read. So how do we do this with common table expressions? So we take this subquery and move it to the start of the statement, use the with clause, and note it's before the select statement. We give it a name, and then we can use this name as a regular table and can reuse it. So now it's easier to see what's going on. The select statement itself is clean and easy to read. And furthermore, we only execute this subquery once. So this version of the statement is twice as fast as the old version. Common table expressions can do a lot more. They can be recursive. You can multiple of them. They're really powerful. So it's something I'll also recommend you to study. So that's the end of the slides, and the remaining time will be used for some Q&A. So one question is why I recommended using a sequential primary key. So this comes down to how InnoDB, which is the primary storage engine in MySQL, is implemented. So you can think of InnoDB as an index organized storage engine. Everything is an index. So the rows are actually stored in a B-tree index called the clustered index. And by default, the clustered index uses the primary key. So if you have a sequential primary key, when you insert data, you just keep adding to the end of the last data inserted. And it's stored in pages, fixed size pages. So when the page is full, you just move on to the next one, and it all comes out sequentially and also stored fairly sequentially on disk. A random primary key, such as UUIDs, they'll insert all over the place and also into full pages, which means that has to be split, moved to other parts of the disk. And that causes random I/O. It causes the the clustered index to become bigger, so there'll be more levels in the B tree. You'll need to read more pages into the buffer pool and so forth. So I know this is a little bit hard to follow this way, but I hope that gives you the idea why sequential primary keys are preferred. So the next question is, what are histograms? And yeah, I mentioned those very briefly. Histograms, you can think of them similar to index statistics, but these are not updated on the fly. There's no index that needs to be updated. So they're very cheap to use. On the other hand, they can only be used by the optimizer to find the correct join order. So you'll never use a histogram together with an index because the index would serve the benefit of the histogram anyway. So that's why I suggest them as something that you could use together with hash joins to get the optimal join order. So there's a question here. What do you mean when saying the functional dependency can prevent the use of an index? So consider a table where you have the birthday for different people, and you want to buy birthday cards for everybody who has a birthday in November. So you could do that by using the month function on the birthday and set that equal to 11. But an index on the birthday wouldn't be able to use this because that indexes the whole date, not just separate parts of it. So in that case, the MySQL would have to say, sorry, I'll need to scan. That said, in MySQL 8, you can actually add a functional index. So instead of saying index this column, you say index the result of applying the month function on the column. And then you can use the index. So have functional indexes in mind. So what are Gray's hash joins? Yeah, so Gray's hash joins is an algorithm for hash joins that implements it using disk, and that's the algorithm MySQL uses for spilling over to disk when the hash join doesn't fit into memory. So the last question here goes back to considering the whole stack. Can it happen that the cause of an issue happens in one layer of the stack, but it's necessary to implement the solution in another? Yes, that can very well happen. And I can actually give an example of this. It was for NDB cluster, so it's a bit different. But there was an issue that there were long stalls. And that was caused by Linux doing memory compaction due to fragmentation caused by the I/O cache. So the cause was really in the operating system, but the solution was to enable direct I/O in MySQL, and that worked around the issue.